Greetings, madam. We are from Group 3 and would like to present our group project in this video presentation. My name is Zezia Joanne, anak Jofrizia, and my group members are Daniel Nasim, Ellen Isam, Justin Joel, and Ronaldin Richard. In this video presentation, there are two sections, which are Part A and Part B. In Part A, we are going to share our analysis on the ARQ protocols and our design for a practical real-world network implementation based on the situation given. The first ARQ protocol is stop and wait. Sender will send one packet and wait for an acknowledgement before sending the next one. If no acknowledgement arrives, which means packet loss, it retransmits the same package. This protocol is simple, but the process takes a long time to complete. The second ARQ protocol is go back in. The sender will send multiple packets at once, and if one packet is lost, the sender retransmits all packets from that point. The pros of this ARQ protocol is that it is faster than stop and wait, which it sends multiple packets at one time. But it wastes bandwidth when it has to resend all the goods packet unnecessarily. The third ARQ protocol is selective repeat. So a sender will send multiple packets but only retransmit the lost ones. Receiver buffers will store the correct packets while waiting for the missing ones. The pros of this ARQ protocol is it is the most efficient one compared to the other two ARQ protocols because there is no wasted retransmissions. But it is more complex because it needs buffer storage and tracking.
Experimental setup. This is the network parameter. This is the first test cases, which is low packet loss and high bandwidth, this is an ideal network. So when we simulate, we got result that in ideal condition, the protocol achieve high throughput with minimal retransmission. Next is test case 2, which is high packet loss, low bandwidth. This is the congested network. So we got result that this case show that how the protocol handles poor network conditions. We also observe that these cases has higher retransmission and lower throughput compared to test case 1. Test case 3, which is high latency network. So in this case, test case, we use two timeout value, which is 100 millisecond and 300 millisecond. So we need our timeout value is different because we want to observe the effect of timeout setting under the high latency. So we got result that increasing the timeout help reduce unnecessary retransmission, but total transmission time is increased. Last but not least is test case 4, which is varying window size. This is only for go back end and selective repeat protocol. In this case, we want to focus on test two different window size, which is the small window of 2 and the large window of 8. Then we got result that increasing the window size improve the throughput and reduce total transmission time, especially under moderate network condition.
Let's start with the throughput. In the other network, stop and wait give us only 8.94 megabytes per second, while go back and achieve 52.2 megabytes per second, and selective repeat, which is 49.42 megabytes per second. As the network degrades, throughput drops sharply, especially for stop and wait, which struggle under high loss and latency. Selective repeat maintains slightly better performance due to its selective retransmissions capability. Next, total transmission time. Stop and wait took the longest in every scenario in high latency conditions, which it reached over 32 seconds. Go back and selective repeat perform faster, especially in the ideal case, taking under 25 milliseconds to transmit 100 packets. Bandwidth utilization was the highest in the ideal network for go backend, around 10.44%, followed by selective repeat. In challenging conditions, both protocols they utilize bandwidth more efficiently than stop and wait, which dropped to nearly zero utilization under high latency. Processing overhead reflects how much our effort was spent retransmitting. Stop and wait hit nearly 30% in the congested network scenario, while go back and selective repeat had lower overhead, which is around 40% and 32% respectively. This shows the advantage of sliding window protocols in reducing protocol inefficiency. The retransmission count really shows the protocol efficiency. Stop and wait required up to 61 retransmissions compared to the 53 for the go back end and only 29 for the selective repeat in the congested network. Selective repeat consistently had required fewer retransmissions due to its targeted resend strategy. And to summarize, selective repeat RQ gave the most balanced performance across all metrics, while go back end performed well in moderate overhead. Stop and wait, though it is simple, it became inefficient in non-ideal network conditions. These results emphasize the importance of choosing the right RQ for the protocol in the network environment. That is all for me. Thank you.
On the topic of analysis and discussion, I'll be explaining on the impact of packet losses, bandwidth, latency, and timeout interval on ARQ protocol. So for packet losses of packets cause retransmission of packets. So more losses equivalent to more retransmission and equivalent to longer total transmission time. Selective repeat have the lowest total transmission time because it sends only the damaged packets. As we can see on the 20% packet losses, we can see that selective repeat has the lowest total transmission time. Moving on to bandwidth, the higher the bandwidth, it will decrease the total transmission time. So stop and wait will have poor performance in high bandwidth, while go back and perform better than stop and wait but still ineffective. However, selective repeat would be the best one because it utilizes all the bandwidth usage by avoiding retransmission. As we can see on the sample on the right side, selective repeat have the lowest total transmission time. On to latency, the high latency increases the total time transmission. Stop and wait would be the most impacted by the latency, while selective repeat would handle the losses better. This is because of the increase the round trip time, which causes the delay. As we can see on the sample on the right side, the selective repeat have the lowest total transmission time, while the highest would be the stop and wait. Finally, the timeout interval. So the longer timeout interval would cause a longer total transmission time. In stop and wait, too short of timeout interval may cause unnecessary retransmission. Selective repeat perform better than both the ARQ protocol. As we can see in the sample again, we can see that selective repeat have the lowest total transmission time.
From our analysis and simulation, we can see that each ARQ protocol performs differently with different network conditions. Stop and go is showing very poor efficiency in high bandwidth and high latency network. Go back and ARQ show improved throughput by sending multiple packets, but the retransmission is causing a bandwidth wastage. Next, selective repeat ARQ show the best overall performance with highest efficiency and lowest retransmission count in high latency network. So to sum everything up, selective repeat ARQ is the most effective protocol between all of these three protocols.
For part B, our situation is to create a network for Narmi Sendirian Berhad, which is the requirement for two offices. Office A will have 15 wired employees, 5 mobile users, and 2 network printers, while Office B have 10 wired employees, 3 mobile users, and 1 network printer. Both offices need guest Wi-Fi in meeting rooms with restricted access. For the objective, we are to design a cost-effective wired and wireless network that connect all employees and devices efficiently, provide secure internet and internal access, separate guest access from internal resources using VLANs, ensures easy management and scalability.
We structured the network around a central Ethernet connection through a secure router which connects to a core switch. From here, we branch off into two access switches, one for Office A and another one for Office B. Office A supports 15 stationary employees using wired PCs and 5 mobile employees using laptops or phones. It also connects to two network printers. Office B includes 10 stationary users, 3 mobile users, and 1 printer, which is all connected via a separate access switch. To ensure a proper wireless coverage, each office has 2 access points, one for the staffs and one for guest users in the meeting rooms. Guests and staff are separated using VLANs to maintain security and prevent unauthorized access to internal resources like printers or PCs. This setup ensures a secure and isolated guest access, a stable Ethernet connection for high-speed workstations, scalable infrastructure using VLANs-enabled switches and structured cabling. In summary, our design is cost-effective, secure, and scalable in fulfilling our Narmin Sedenberhat's operational needs with separate paths for staffs, guests, and devices. That is all for me. Thank you.
For our networking hardware equipment, for wired connection, we will be using Cat6 UTP cable. And for router, we have chosen MikroTik Hex S router. Then for core switch, they will connect both of the office switch will be Netgear GS728TP switch. So for wireless access point, which will be used for mobile phone or any wireless device to connect to our network, is TP-Link EAP245. And then for office switch, we decided to choose TP-Link PL SG1024DE because it have 24 port, which is more than enough for our network, for our office device requirement. So I will explain about inter-office connection using Cat6 unshielded twisted pair cable. So first, the justification of using Cat6 UTP is fast and stable connection. Cat6 can support up to 1 gigabit per second and even 10 gigabit per second over short distance, which is ideal for the office environment that we are going to implement this. Next, wired connection also less prone to interference such as wall and other network and microwave. So that means the connection will be very stable. So there is no interruption when we are using the network. So next, the low latency of Cat6 enable office worker to do tasks such as voice over internet protocol, file transfer, or remote desktop work, which improve overall experience by minimizing the delay for office worker. So worker can work efficiently with faster network and low latency. So next, the security wired network is much harder to be intercept compared to wireless connection. So it reduced the risk of unauthorized access. So next, cost effective. Cat6 UTP is more affordable than fiber optic, and it is sufficient enough for the office deployment. In this case, it will connect both um, network within floor or two floor, and then the installation is also simple, and the maintenance will be easy due to the wide availability of the cable. So the cable can be easily be get from um, online or hardware shop. So in case of office expansion, the scaling will be easy because uh, Wired network is not as complicated as wireless one. So that is all from me.
Next is wireless network for employee and guest access. This connection is for Wi-Fi 6 or Wi-Fi 5. So the reason we need to use the wireless is because it has better coverage and device load balancing, which it can cover the whole office and balance the device connection. Next, wireless also has secure guest Wi-Fi with SSID segmentation and VLANs, which is this can protect the staff network from the guest device. Wireless also provide mobility and flexibility, so staff or guests can connect wirelessly from anywhere in the office. Last but not least, wireless also easy to deploy and scalable. So it's quick to install and it also easy to add more apps, APS if needed.
The preferred connection for all the printers is wired. This is because it can prevent Wi-Fi congestion and to make sure all users have stable access at all times. Some of our cybersecurity recommendation for this company is to have the guest Wi-Fi on separate virtual LAN with no LAN access. Next, we can also enable the media access control filtering and Wi-Fi protected access 3 or 2 on all wireless networks. That is all from our group. Thank you.